Hi, and welcome to Dr. V's AP Chemistry webcast. I'm Dr. V, and I'm here to discuss photoelectron spectroscopy with you. What I'd like to talk about first is to do an overview of the principles behind photoelectron spectroscopy. And then I'd like to talk about how to interpret PES spectra. And I'd like to wrap up with a practice problem. Just to refresh your memory, ionization energy is defined as the energy it takes to remove an electron from an atom. Now, we often talk about the first ionization energy, the energy it takes to remove the outermost electron from an atom. But with photoelectron spectroscopy, we can actually look at ionization energies of inner electrons as well. We know that electrons that have a stronger Coulombic attraction to the nucleus will have a larger ionization energy. One important factor in this is the distance from the nucleus. So an electron in energy level 1 will have a very strong Coulombic attraction to the nucleus because the distance between the electron and the nucleus isn't very large. An electron in energy level 2 is farther away from the nucleus, and because of this greater distance, would have a weaker Coulombic attraction to the nucleus. Therefore, it's going to take more energy to remove an electron from energy level 1 than it would from energy level 2. Let's say we have a lone hydrogen atom. We've got a Bohr level representation of that. And let's talk about how PES works. We're going to bombard the atom with high energy photons. When the photons bombard this atom, which is probably a gas phase atom, the photons can cause the atom to release an electron. So the photon comes in, it interacts with the electron. If it's got enough energy, the electron will actually leave the atom. We call this a photoelectron. We're going to bombard the atoms in the sample with photons that all have the same energy. But what if the photons are really low energy? What will happen then? Well, if the photons don't have enough energy to overcome the Coulombic attraction between the electron and the nucleus, we're not going to get a photoelectron. Nothing's going to happen. It just doesn't have enough energy to overcome that attraction, and the electron will not be ejected. We need high energy photons. Now, high energy can mean different things. It can mean X-rays, it can mean ultraviolet light, it can be high energy visible light, depends on what kinds of electrons we're trying to eject from the atom. But if they are high enough energy, we can get that photoelectron to be ejected. We know the photon's energy, we know E equals h nu, so the photon energy is coming in, and if it is greater than the ionization energy, the photoelectron will be emitted, and we can actually measure its kinetic energy. The difference of the energy of the photon and the kinetic energy of the electron is equal to the ionization energy when we're working in the gas phase. And so we can actually use this to find ionization energies. And if we're using X-rays, we can eject inner electrons or core electrons. We can use visible light or ultraviolet light to eject valence electrons. And so we can use photoelectron spectroscopy to figure out the ionization energies of all the different electrons in the particular atom that we're looking at. How are the photoelectron spectra affected if we have more than one electron in an energy level? Let's say we have 2 electrons in energy level 1. Well, the photons are coming in. They can strike the first electron and emit it as a photoelectron. They can eject that second electron, which has the same ionization energy. We're going to get twice as many photoelectrons being ejected. So when there are multiple electrons occupying the same energy level or sublevel in that atom, we're going to see a proportional number of photoelectrons being ejected that have that same kinetic energy. If there are multiple energy levels occupied by electrons in a particular atom, what we're going to see is that photoelectrons with different kinetic energies will be ejected from the atom. The light comes in, it ejects an electron from energy level 1. That same light is coming in, hitting another electron from energy level 2 and ejecting it as a photoelectron. But these 2 photoelectrons are leaving with different kinetic energies. We know that the ionization energy of electron number 1 in energy level 1 is greater than the ionization energy of the electron in energy level 2. Because we're bombarding the atom with high energy photons, all of the same energy, what we realize is that the kinetic energy of photoelectron 2 is greater than the kinetic energy of electron number 1. And we can measure these and compare them. In AP Chemistry, the real emphasis is on interpreting PES spectra. What do they tell us about the arrangement of electrons? What do they tell us about ionization energies? What do they tell us about electron configurations? The x-axis of the PES spectra really gives us the binding energy, or in other words, the ionization energy. How strongly attracted is that electron to the nucleus? Let's look at a PES spectrum for the hydrogen atom. Now we know that hydrogen has 1 electron. We know that it's in the 1s orbital, and its position on the x-axis tells us the ionization energy. Of course, there's only one proton also for that hydrogen. So what this is telling us is how strong is the Coulombic attraction between the electron and the nucleus. The x-axis in PES spectra often runs in reverse, so the larger value may be on the left and the smaller values may be on the right. This isn't universally true, so always check your axis. And sometimes the spectra are given with a break in the axis as well, so just pay attention to those little details. Because of the way PES works, it means we end up with a peak for each occupied sublevel. In fact, this was evidence for sublevels found long after the modern model of the atom was proposed, but it does back it up very nicely. So if we look at our PES spectrum for hydrogen, we see one peak because there's only one occupied sublevel in hydrogen. That one electron is in the 1s orbital, and we get one peak. In a given PES spectrum, whichever peak has the largest binding energy is going to be closest to the nucleus. So that's always going to be your 1s sublevel if it's a complete spectrum. So once you've identified the 1s sublevel, you can use the Aufbau filling sequence to identify the other peaks, because they're going to go in order of decreasing energy. I'd like to compare the PES spectra for hydrogen and helium. Now we know that as nuclear charge increases, the binding energy increases. You're going to have a stronger Coulombic attraction between those electrons and the nucleus as the nuclear charge increases. So when we compare these spectra, hydrogen spectrum is in pink, the helium spectrum is in blue. Both of them have electrons in the 1s sublevel. But if we look at hydrogen, that has one proton, helium has two protons. And notice that the 1s orbital in helium has a higher binding energy than the 1s orbital of hydrogen. And that's because the 1s electrons of helium experience a stronger Coulombic attraction to the nucleus than the 1s electron of hydrogen. And so we can use this to figure out which peak is which. That's why the peak for helium has a higher binding energy than the peak for hydrogen. The other thing I need to point out about PES spectra is the y-axis. The y-axis gives the relative number of electrons in each occupied sublevel. It's going to be proportional to the number of electrons occupying that sublevel. So what we see is when we look at the hydrogen peak versus the helium peak, right? Hydrogen has one electron in that 1s sublevel. Helium has two electrons in the 1s sublevel. So the peak for helium is twice the amplitude of the peak for hydrogen. Now let's look at the PES spectrum of neon. We know that neon has the electron configuration 1s2, 2s2, 2p6. How is this reflected in our PES spectrum? We know the x-axis gives us the ionization energies of the different sublevels. And the sublevel with the highest binding energy is going to be the 1s sublevel. There are three peaks in the spectrum because there are three occupied sublevels in our electron configuration. So we have our 1s sublevel, we have our 2s sublevel at a lower binding energy, and then our 2p sublevel. And we know the y-axis tells us the relative number of electrons in each sublevel. We know there are 2 electrons in 1s, 2 electrons in 2s. Notice that those two peaks have the same amplitude. The 2p sublevel has 6 electrons compared to the 2 electrons in the s sublevels, and notice that that peak is 3 times as high as the other two peaks. And so it all fits together very neatly to support the electron configuration of neon. Let's wrap this up by doing a problem. A complete PES spectrum of an element is shown. Identify the element and write its ground state electron configuration. Now, the fact that this is a complete PES spectrum tells us that all the occupied sublevels are here and represented in the spectrum. The first thing we need to do is find the 1s sublevel. That's going to be the peak with the highest binding energy, right? And so that's our 1s sublevel. Next comes 2s, then 2p, then 3s, and after 3s comes 3p. So we can identify all the occupied sublevels in this element. It's very evident that the 2p sublevel is 3 times higher than the 2s sublevel. We're assuming that the 1s sublevel is completely occupied, the 2s sublevel is completely occupied. Since the 2p sublevel is 3 times higher, that's also fully occupied. We are writing a ground state electron configuration, so that seems very reasonable. I notice that the 3s sublevel has the same amplitude as the 1s and 2s sublevels, but the 3p sublevel is only half the height of the 3s sublevel. So if the 3s sublevel has 2 electrons, the 3p sublevel can only have 1 electron. And that means this must be aluminum. And the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. We study PES spectra in AP Chemistry because it gives us experimental evidence to confirm ionization energies and electron configurations. Remember, when you're looking at PES spectra, the x-axis gives the binding energy, or the ionization energy. You have a peak for each occupied sublevel, and the peak with the largest binding energy is closest to the nucleus. That would be your 1s sublevel. As the nuclear charge increases, the binding energy of all your peaks increases as well, because they're going to have a stronger Coulombic attraction to the nucleus. The y-axis gives the relative number of electrons in each occupied sublevel. And so you can use that to figure out how many electrons occupy a given sublevel. The more electrons in the sublevel, the higher the amplitude, and it's all proportional. We can interpret PES spectra to determine electron configurations and identify elements. And that's how we use PES spectra in AP Chemistry. If you haven't already, subscribe to my channel so you get all my latest videos. Like the video, leave a comment, and study chemistry every day. That's how you get better.